Okay, while we're waiting to get started today, if you're interested, we've been talking a little bit about antigenic evolution and viruses. I developed this game called Vaxcraft, which you may have noticed this thing at the front as well, which is like a physical version. I use it to educate children about how viruses evolve. So we'll see different shapes here. And this virus corresponds with antigens. These are things that change. Have seasonal flu viruses. It's the reason why when Omicron came into the population, it was able to evade previous immunity from Delta variant. So there's this game online. You can play it at vaxcraft.thenTrythis.org. I can send around the link as well. And the idea is that you are trying to protect these little creatures against an evolving virus. So you have to vaccinate against these different shapes. So these different shapes here are squares. So if I vaccinate against squares, then they'll be more protected. So underlying all of this, there's mathematical models, types of models that we'll be talking about later in this course. And as we've been thinking about antigenic evolution and these antigenic cartographies that have been in the notes, this is essentially what's going on here as well, right? The viruses will be evolving in response to changes in the buildup of immunity in the population. Okay, anyway, we'll start in a few minutes. I just wanted to mention that in case you guys are interested. Okay, good morning, everyone. I'll make a start. Okay, can I just have a quick show of hands who watched the pre-lecture material? Okay, good. Thanks very much. Okay, so as you'll know, today we're going to be talking about vectors. These vectors are super important things, mathematical tools that we can use to represent data. They can be used to represent magnitudes and directions of things as well. So they differ a little bit from the types of numbers that you're used to, scalars, that are just, say, real numbers. So we're going to talk a little bit about why vectors are useful and how we can manipulate those vectors and how we can do some algebra with them as well. So in the context of some biological problems, why do we care about them? Well, going back to this idea of antigenic evolution in viruses, well, we might want to quantify how viruses change year to year and over longer periods of time. So to do so, because we're in more than one dimension, we have to maybe quantify not only how much a virus has changed from one year to the next, but also in which direction it's changed. Okay, so things in this map up here, they tend to be moving roughly down, but they're also moving a little bit left and right. Okay, so we want to understand if, say, we've moved 3 units, whatever those units happen to be, have we just moved 3 units down? Have we moved a bit diagonally? And the reason this will matter is because year on year, if you're zigzagging, then there'll tend to be a bit more similarity overall. Whereas if you're just moving in a straight line, things will move further and further away from each other. Okay, so we care about vectors in this kind of context. We can also think about them in terms of how if you recall, at the end of the last lecture, we looked at irises and a measurement of a new flower. We can do similar things by trying to decide how an observation of a particular plant or an animal matches our measurements. Now, you might want to do that by looking at the distance, by measuring different characteristics, like in the case of the flowers, what are the lengths of, say, the petals, and compare all of these different things, come up with a distance measurement and say, well, this one is most similar to this one. But things might be growing as well. So maybe you care about the direction and how they're changing in proportions. And we can look at them then in terms of vectors as well. And so we can have different ways of making these similarity comparisons. Okay, so just to quickly go through the pre-recorded lecture material, I introduced vectors. So vectors have both magnitude and direction. Okay, so a scalar is just, say, a single number, whereas a vector will have at least 2 components to it, right? It's always going to have some magnitude and some direction. So examples of scalars: height, speed, distance. You know, if you travel at 3 meters per second, or if you're 1.8 meters tall, those are just scalars. Whereas something like velocity, so velocity is speed plus a direction. Okay, so if I'm walking at 1 meters per second in this direction, then that's a velocity. If I just say I'm walking at 1 meters per second, then that's a speed, it's a scalar. Okay, so there's a bit of notation there. So we tend to write vectors as letters with a little arrow over them. Sometimes you'll see them in textbooks as being in bold. The notation can vary a little bit, but if you see a letter with a little arrow over it, that will mean that it's a vector. And because these are things that have both magnitude and direction, it's easy to think about them in terms of arrows. Okay, so an arrow has a certain length, it has a direction that it will point in. Okay, so you can think of its initial point, its terminal point, and that as being our vector. And we can do algebra on vectors just like we do with scalars. We just need to be a little bit careful with how we combine these things. Okay, so if we've got these two vectors here, u and v, and u points from point A to B, and v points from B to C, then if we add u and v, it's just like you're walking along the path with the arrows. So that's the same as the vector w. Okay, so if I say walk 5 units in this direction, and then 4 units in this direction, that would have been the same as me just going 3 units in this direction. I know that because it's a Pythagorean triple. Okay, so we can add them together and just think about them as being paths, and you're just following where these arrows go. So vectors, we can think about them as joining points to points, but we can also move those vectors around. Okay, and because we can move them around, when we add them together, in this case, if we add v and u, we can think about either adding u or following u, then v, or following v, then u. We still end up at the same point. Okay, so it doesn't matter which order we add them in. The key thing is that because these vectors have components, so they have, say, an x component, a y component, maybe a z component, and so on, we have to always add the components with their matching ones. So add the x's together, add the y's together, add the z's together. We can also multiply vectors by scalars. So again, a scalar is just a normal number. In this case, if we have a vector u and we multiply it by a scalar, which is 4/3, we're going to extend that vector by a factor of 4/3. Okay, so it's a little bit longer than the previous one. So all you need to think about here is a scalar multiplication is just like stretching or shrinking and potentially flipping around a vector. So if c was negative, as in the second example on this side here, then we flip the direction as well as maybe stretched it or shrunk it. Okay, so think of this arrow. Your scalar is stretching it, shrinking it, maybe flipping it around, but it would still be pointing along a straight line that it would have been pointing it in originally. Okay, so we talked a little bit about components as well. I'm not going to dwell on this too much. Again, a little bit of notation. I'll try to keep this notation points as being having round braces, and vectors, I'll tend to write them as having these triangular braces. I will occasionally do square ones. Sometimes the notation will differ between different places. Try to understand what it is based on the context, maybe rather than the notation. I'll try to be as consistent as I can. I'll skip over that. And that, I don't think we need to do that. The length of a vector, well, you can think of this as just being like our straight line examples of how we work out the distance between 2 points. It's got a direction. The direction doesn't matter for distance, right? Because we just care about if it's length 2 in this direction, it's exactly the same as being length 2 in this direction. Okay. So we use our Pythagorean formula. So we have we make a right angled triangle. It doesn't matter how many dimensions we're in. We do exactly the same thing. We take we square each of the components, add them together, and then square root them. If it's in 3 dimensions, then we square all of the components and so on. So that is relatively similar to what you did before in terms of distance. And there was a little bit at the end about a bit more algebra in terms of, we can add, we can subtract them, we can do scalar multiplication, and this is what it does to the different components. Okay, any questions about any of the pre-recorded lecture material? Nope. Okay. In that case, we'll get started on some problems. So what I want to do to start with is just get you guys thinking about different types of scalars and vectors. So have a moment here, chat to your neighbor, think about a couple of examples of scalars and a couple of examples of vectors. Okay. And don't just go with the ones that I gave before in the pre-recorded lecture. Try and think of some other ones. Okay, let's see what you guys thought. Okay, let's come back up. Sorry, I was having a few tech issues there. Okay, can I have, first of all, a couple of examples of scalars, please? Width, yep, so width of an object, doesn't matter which direction you're looking in, it's still the same width, yep. Time, yep. Frequency, yes, we don't care about any direction there, so that's fine. So these are some good examples. Sorry, someone else had a hand up? Temperature, yeah, great. These are all examples of scalars. How about vectors? Yep. Velocity, yeah. So we have a speed and a direction. So we put those together and we get a velocity, yeah. Acceleration, yeah. So this is just like velocity, but it's the derivative of velocity. So we care about whether you're accelerating or decelerating. So acceleration is opposite to your deceleration. So they might be the same length, but they'll have the opposite direction. Okay, so good examples as well. Any other examples? Yeah. Momentum. Ooh, momentum. I guess, yeah, if you're going in a particular direction as well, yeah, that's fine. Does someone else have their hand up here? Sorry? Displacement, yeah, so you've got a direction as well and a magnitude. So these are all great examples. How about these are the three at the bottom? So the current in the river, is this a scalar or a vector? Vector, right? So current has direction and magnitude. You care if you're going upstream or downstream. The rate of population growth in Canada. Scalar. So it's a rate, but this one's a little bit tricky actually, because you could have negative population growth. So it could, in theory, be a vector, but we'll classify it as a scalar here. Direction from your house to SFU. Vector. Depends if you're looking, say, just on a 2D map and you said, okay, my house is here and SFU is over here. That would just be a direction and you wouldn't care about the magnitude, right? But if you're thinking about a 3D map and say, my house is here and SFU is up the hill, then I've got to go in a direction that has two components. Okay, so now we would describe this as a vector. Okay, let's move on. So let's think about vectors as directed line segments. Okay, so in other words, as arrows. So we want to here find a vector u given by a directed line segment AB. So A starts at the point -1, 3, B starts at 7, 2. And we want to draw an arrow between those that it corresponds to our vector u. So what does that look like? Okay, so if we call this, let's do -1, sorry, ignore that completely. 0, 1, 2, 3, -1, -1, 1, 2, 3, 4, 6, 7, 8. Okay, so A is going to be up here, -1, 3. B is 7, 2. So it's down here. I'm going to draw a very dodgy looking arrow between them. So this is A, this is B, and this is our vector u. So the second part is to draw this equivalent vector starting at the origin. So like I said earlier, although we can think about them as being defined by a start and an end point that are potentially fixed, here are A and our B, there's nothing special necessarily about that A and B defining this vector, okay? We could just pick that vector up and move it around the screen. Okay, so if we want to start at the origin, well, what do we know about this vector? Well, we know that we go down 1 unit and we go along 8 units. So we could draw exactly the same vector, I'll do it in different color. It's going down 1 unit and along 8 units. We call this point C. So this vector is still our vector u. we've just moved it around the screen, and that's fine. We can just pick it up and move it around wherever we want to. So I mentioned math3d.org the other day. If you don't have time to copy down all these solutions, don't worry, they will be posted online. So I mentioned math3d. Again, if you want to have a feel for what it's like to have vectors and to manipulate them, have a go at trying to plot some of the vectors, especially from some of these examples on math3d.org. And you can think about what it means to be a vector and how we can manipulate them, how we can work out their lengths and things like that. Okay, so I'll leave that to you guys as an exercise. Okay, I want you guys to just have a quick practice at calculating vector sums and then illustrating them geometrically. So drawing what these arrows look like. Okay, so find the sums of these vectors here. So let's call this, should change. Let's call this vector u and this vector v. In the second example, we'll do the same, okay, u and v. So work out u plus v in each of these two cases, and then draw them geometrically. Okay, have a go at that, and I'll walk around and give you guys some help. Okay, let's see how you guys got on. So first of all, I'm going to add together these things component-wise. So A, we've got u plus v is going to be -1, 4 plus 6 minus 2. We just add the components together. So we're going to have -1 plus 6. So we're going to have 5. 4 minus 2 is 2. So this is going to be our vector here. And let's see, if I start drawing it, oh, I'm going to run out of space here, so I'm just going to erase this. So we're going to want a vector that's 5, 2. So what does u look like? Well, I go left 1 unit and up 4 units. So u could look like this. Imagine that's actually a straight line. And then v, we're going right 6 units and then down 2. So 1, 2, 3, 4, 5, 6, and then down 2. So it should go to here. I'm going to do that in a different color. So our vector v. So our vector u. And then our vector, let's call it w, is the equivalent of just going from the initial point of u to the terminal point of v. Note that the order doesn't matter here. So suppose I started off at this start point and I followed v first of all. So I went down 6 units, sorry, right 6 units and down 2. I'd have gone to here. So that's v. And then if I follow u, I'd have gone up here. Again, it's exactly the same, right? So sometimes these geometric arguments can help you visualize what's going on and understand the underlying algebra, okay? So this is, we end up with a parallelogram here. And our diagonal, this main diagonal here, w, is describing the addition of those two sides, okay? So follow u, then v, or follow v, then u. We end up going from the same start point to the same end point. Okay, so that was part A. Part B, where our addition is going to be u plus v is equal to -2 minus 2 plus -2, 4. So we have -4, 2. So what does that look like? Again, let's follow u, then v first of all. So suppose we start up here. U is -2 minus 2. So left 2 units, down 2 units. V, we're going to be going left 2 units and Oh no, I wanted to do the other way around, that's why. I'm going to start off with V first, otherwise I'll run out of space here. So ignore the fact that I've got a U there already. Let's start off at V. We're going left 2 and up 4. So that's my V. Let's draw it as a straight line rather than a wonky line. Okay, I'm just going to do these the other way around this time, just because otherwise I'll run out of space. So we start at the bottom of V. We go up 4 units and left 2 units. Then we follow U. We go left 2 units, down 2 units. This is the same as if we had just gone from the start point of V to the end point of U. That's our W. And we could have done these things the other way around. We could have followed U first. So remember, that's down 2, left 2. And then followed V. So left 2, up 4. Again, we've got a parallelogram here, and that diagonal is telling us what the addition is. So this is one way of thinking about how we can add together vectors and what they look like when we try to illustrate them. Obviously, this is easy to do in 2 dimensions. When we have many more dimensions, we can't visualize what that looks like, but hopefully it gives you an idea what to do when you've just got 2 dimensions. Okay, can I just have a show of hands who managed to do that? Okay, a few of you. There's a question there as well, yeah? Sorry, say that a little bit louder. Yep, so that's exactly what I did up, if I highlight this bit up here. I've just added the -2 and the -2 to give me the -4, and then -2 plus 4 to give me the 2. Sorry, a little bit louder. Well, in this particular question here, we haven't got an origin, right? We've got this graph paper that's, we don't, I'm defining each one of these squares as being 1 unit. We can pick them up and move them around, right? That's why we end up with these parallelograms, because it doesn't matter where we're, as long as we're consistent with how we're linking these things up, that we don't have a gap between our U and our V when we're following those arrows. It doesn't matter where we start and where we finish in terms of the origin. But yeah, you can translate them to the origin, that's fine. And if you did that, then for example, for the second one, you would end up at point -4, 2 if you started at the origin. So that's another way of thinking about this. If you've got a vector with components, say A and B, whatever those A and B happen to be, that could be, that's the equivalent of starting at the origin and going to point AB. Okay, so you can move them around and place it at the origin, and that is the point that you would end up at if it started at the origin. Okay, but it doesn't have to start at the origin. Okay, oh, we don't have time. Okay, we've got about 20 minutes. So I want to go back to this idea of antigenic evolution and thinking about how we can use vectors to understand something about how viruses are changing. So this is the zoomed in portion of that antigenic map that we've looked at a couple of times already, going from 1989 to 1995. Each of these little clusters is essentially a group of samples of different viruses. And remember that this was originally in, I think, 79 or 73 dimensions and was condensed down to 2 by using projection. We don't really care what these left and right directions actually mean for our purposes here, but it's measuring some degree of change, okay? So we think of all of these ones in 1989 as being fairly similar, and then there's some kind of jump to 1992. Again, most of those are fairly similar, and we can group them here as they are grouped by colors as we progress through time. So how can we maybe classify some sort of change? One way of doing that is to start by thinking about these yellow dots here as some kind of central point. So we talked the other day about drawing circles or spheres in some space by putting a central point, and if you have a stick and drawing a line in the sand as you turn around, that will turn into a circle. We could do a similar thing here by picking a central point where we're kind of minimizing the distance to everything. So let's call this point P here. In pink, hopefully you can see that. This one Q for 1992, and this one R for 1995. Okay, just giving them some labels, the points that are in the middle of those clusters of viruses. Okay, so we want to think about some of these questions here. So I'll move on to these ones here. So we've got some actual numbers to attach here. So remember we called the first one P. So these are just the coordinates of our point P. This one's going to be Q. And this one here is going to be R. Now I'll go through with you guys here the concepts of how we solve them. I'll leave you guys as an exercise to go through and actually plug in the numbers and try and work out, make sure that you get the right numbers, and then you can check those against the solutions, okay? I don't want to waste too much time in class plugging numbers into calculators if we can avoid it. Okay, so what vectors represent the change from 1989 to 1992, and then from 92 to 95? So what is the vector that represents the change from 1989 to 1992? Yeah, P to Q, yeah. So we can call this whatever we want to, but let's call this a vector U. It's just going to be P to Q. So remember, this is the other way that we can write a vector. If we've got 2 points, here PQ, we just put PQ and then an arrow between them, which tells me that I've got a vector joining P to Q. How about 1992 to 95? I've heard murmurings. Someone shout out, Q to R? Yeah. Okay, so those are our vectors. So what do they look like? Let's go back to this map here. So we've got P to Q. It's not a very good color. Let me find a better color. Try black. Okay, P to Q. Remember, this is our vector U. And then Q to R, that was our vector V. So the sum of those vectors, wow, again, I want you to, in your own time, go through and add these together and make sure that you remember how to do component-wise addition for our vectors. The sum is just going to be U plus V, right? So we've got our components for U, our components for V. Well, we have to work out what those are first of all, right? Because we've got our points, but these things here, these are points, not vectors. So to work out what our components of our U and our V are, we need to take our terminal point. So for U, that's going to be Q. And when we subtract our initial point, P. So we do Q minus P, and that will give us our components for our vector U. And then for our vector V, our endpoint is R, and our start point is Q. So again, we take the endpoints R, we subtract the initial points Q, and that will give us our vector V. So once we've worked out what those vectors are, remember those vectors are just telling us a direction and a magnitude, and they can be moved around wherever. If we anchor them at P, Q, and R accordingly, then we can add those vectors together, and that will give us the change from 1989 to 1995 directly. So this is the answer to here. If we call this, say, W, that's going to be our addition of vectors U and V. So going back to this here, I'll use blue this time. So if we wanted to jump straight from 1989 to 1995 or quantify how much has changed between these years, this is our vector W, which is equal to U plus V. How about the vector representing change from 1992 to 1989. What's this going to be? So we're going backwards in time now. What's this vector going to be? So in 1992, we're starting at Q. 1989 is P. So let's call this vector, I'm going to call it S for now. S is going to be the vector from Q to P. So you can work out what this is, but this is just going to be minus P to Q. That was a very dainty sneeze, which is equal to minus U. Okay. So because we've gone back in time, rather than going from P to Q, we're going from Q to P. We just put a minus sign in front of it. And we end up with minus U. Okay, and that should make sense. Again, if we think about these things geometrically, if we're starting off here at Q, and we want to go back in time to here, we just need to follow our U vector, but going in the opposite direction. Okay, so this is minus U. So just think you've taken the arrowhead and you put it on the other end. Okay, any questions about that? I appreciate I've not gone through the numerical side of that, but like I said, that's time. I think if you want to consolidate that information, make sure you understand how you do the components, do that out of class and check against the solutions. Here, I just want to make sure you understand the concepts of how we combine these things together. Any questions on that stuff? Yes. Yeah, so on the Canvas page, on the course schedule, after class, I'll post these solutions. So the solutions from Friday were up on Friday. Likewise, I'll do these because sometimes in class as well, we won't have time to go through all of these questions, but I put some extra ones in there for you guys to look through and work on, okay? It's okay? Okay, one more question, guys, and then you are free to depart, I think. Oh no, there's a couple more questions. We'll see if we get through both of them. Okay, there's a question on the instructor questions about biomechanics. So that sounds a little bit scary. Biomechanics, I think it really is just about forces acting on the body. So if we've got a sprinter who's starting in the blocks, they have some forward acceleration, but they also have some upward acceleration because they're crouched down when they start. So we can think about those as being vectors, right? So they've got some force that's going up and they've got some force that's going forwards. And we want to work out, well, what is their total? What's their resultant force? And that's going to be some combination of these two things, right? So the resultant force vector, well, have a go at doing these. I'll walk around. So we've got these two vectors here. We've got 490 newtons going up. We've got 180 newtons going forwards. Work out what the resultant force vector is and what is its magnitude. So in this case, its magnitude is going to be its length. Okay. Again, I'll walk around and answer any questions you guys might have. Okay, let's run through this before the end. So what is the resultant force vector? I saw a few people are a little bit confused by this because we've got our arrows both starting at the same point. And so I saw quite a few people doing something like this, or going in the other direction, right? And that's fine. Quite a few people did this. So if you did this, you're not alone. It's always good to make a sense check, and a few people thought this didn't look quite right. If we think about this guy, he's moving forwards and up. So the sniff test of this should be our resultant force should point in the direction that he's going to be going. Okay, so we know that it should be going up and to the right, something like that. The key thing here is that remember our vectors, if we're adding them together, we're putting initial point to terminal point, initial point to terminal point. So you're following the arrows, okay? Here, the arrows both have the same initial point, but we can pick this one up here and move it over to the right here. Now we're following initial point here to terminal point, initial point to terminal point. So that means if we draw our resultant force vector, I'm going to call this one F1, this one F2, and then I'll call this just F. Okay, I've used capitals here, but it doesn't really matter too much. Okay, so this is our resultant force vector. If we were to write that in component notation, well, our F1 is equal to 180 newtons to the right and 0 up. Our F2 is 0 to the right and 490 newtons up. F is equal to F1 plus F2. So we just add the components together, which is 180 and 490. Okay, that's our resultant force. So it's always good, like I said, to do that sniff test, that sense check, whenever you're looking at a biological problem. Okay, does it seem to make sense? If you don't think it makes sense, go back and check it. Okay. What is the magnitude of the force? The magnitude of this force is just going to be its length. So the magnitude of F is going to be its length. That's the square root of 180 squared plus 490 squared, which I believe should be something around 522 newtons, roughly. Can I have a show of hands who managed to get those two components? Okay, great. That's it for today. I'll stick around for a few minutes if you have any questions.